Welcome, welcome, welcome to another deep dive. Today, we're cutting through the noise and taking a shortcut to being truly well-informed on a topic that sits right at the heart of how we build the world around us, molecule by molecule. Our mission today is to demystify some truly foundational reactions. We're drawing from a comprehensive chapter in Advanced Organic Chemistry, Part B Reactions and Synthesis, 5th edition, specifically focusing on how chemists precisely build complex molecules, one carbon-carbon bond at a time, using compounds of three fascinating elements: boron, silicon, and tin. Why does this matter to you? Well, imagine trying to build a complex Lego castle, but you can only connect one specific type of brick at a time, and you need to ensure every connection is perfectly placed in 3 dimensions. That's essentially what chemists do when they make new molecules. Understanding these reactions is like peeking behind the curtain of drug discovery, enabling the creation of life-saving medicines.
Absolutely. Yeah.
It's crucial for developing new materials with incredible properties, and it's even how we synthesize complex natural products found in plants and organisms. These 3 elements are indispensable tools in a chemist's arsenal, and by the end of this deep dive, you'll grasp not just what happens in these reactions, but why they are so vital for innovation and how chemists achieve such extraordinary control.
And we're going to make sure this isn't just, a list of facts. Our goal is to clarify any technical terms, dissect the fascinating molecular dances, the mechanisms that govern these transformations, explore the clever synthesis strategies chemists employ, and really highlight their practical applications.
Right.
We want to ensure you don't just hear the information, but truly understand the intricate ballet of atoms and electrons that makes creating new compounds possible, helping you feel truly well-informed in a concise and engaging way.
Okay, let's unpack this. Our journey begins with these 3 seemingly unassuming elements: boron, silicon, and tin. They sit at this incredibly intriguing non-metal boundary on the periodic table, right in that gray area.
That sort of diagonal line, yeah.
Exactly. And it's precisely this ambiguous positioning that grants them such unique properties for orchestrating carbon bond formation. You see, their electron configurations and bonding behaviors are a bit different from your typical metals or nonmetals, giving them a special, almost chameleon-like role in organic synthesis.
What's particularly fascinating here is their fundamental difference from, say, transition metals like palladium, which we've talked about before. With transition metals, the metal often undergoes a change in its oxidation state during the course of a reaction, acting as a dynamic participant that cycles through different electronic states. Boron, silicon, and tin, however, typically don't change their oxidation state.
Oh,
Instead, they act more like sophisticated delivery vehicles for carbon substituents. Think of them as specialized trucks that bring a carbon group along with its associated electrons to a reactive carbon center. For this particular deep dive, we're going to keep our focus squarely on reactions, where these carbon groups behave like electron-rich particles, nucleophiles, not the radical or single electron kind.
so if I'm understanding this, these elements aren't undergoing the dramatic electronic transformations we see with, say, a palladium catalyst.
Oh, usually no.
Instead, they're essentially high-precision carbon delivery systems. They bring a specific piece of carbon, along with its electrons, to a particular spot where a new bond needs to form. And our source material really emphasizes their role as sources of nucleophilic carbon groups, meaning carbon groups that are electron-rich and ready to donate electrons,
Right, electron-rich attackers.
which then attack electrophiles. These electrophiles are electron pore centers, often a carbon atom that's part of a carbonyl compound. Imagine a carbonyl group, which is a carbon double bonded to an oxygen, as a highly reactive electron-hungry site, just waiting for a nucleophilic carbon from boron, silicon, or tin to come along and start building something new.
Precisely. And a particularly important class of derivatives for all 3 elements are the allylic ones. These are compounds where the metal is attached to a carbon that is directly next to a carbon-carbon double bond, giving them a special kind of reactivity that chemists leverage for very specific transformations.
Allylic. So that double bond nearby is key.
Absolutely. It plays a direct role. Let's look at how each one typically operates. First, with allylic boranes, these compounds leverage boron's unique Lewis acid character. Think of a Lewis acid as an electron magnet boron, being electron efficient, readily accepts electrons. When an allylic borane encounters a carbonyl group, the boron cozies up to the carbonyl oxygen. This interaction effectively makes the carbonyl carbon even more electrophilic, more hungry for electrons, and at the same time, it weakens the carbon-boron bond, priming it for action.
Okay, so it activates both ends in a way.
Exactly. What happens next is quite elegant. The electron-rich allylic group adds to the carbonyl via a clever cyclic transition state. You can imagine this as a small, temporary, six-membered ring forming during the reaction, which guides the precise alignment of the atoms.
A temporary ring, like a little jig for the atoms.
Sort of. And this highly organized temporary ring also leads to a 1-3 allylic transposition. What that means is the double bond in the allyl group effectively shifts its position during the reaction.
Ah, so it rearranges itself.
It does. You start with the boron attached at one end of the allyl system, and the new carbon bond forms to the other end, with the double bond moving into the middle. It's a very predictable and controlled rearrangement that is incredibly useful.
Right, predictable control is the name of the game here.
Now, allylic silanes and stananes operate a bit differently because silicon and tin have less pronounced Lewis acid character compared to boron. These compounds typically react with various electrophiles through a process called demetallation.
Demetallation, so the metal just leaves.
Pretty much. The silicon or tin group simply leaves as the new carbon bond forms. They are exceptionally good at delivering those allylic groups, not just to carbonyls, but also to iminium centers.
Iminium centers, those are the nitrogen ones, right? Carbon-nitrogen double bonds.
Exactly. Highly reactive Cm+ systems. Often crucial for building nitrogen-containing ring structures, which you find in tons of natural products and pharmaceuticals. The leaving of the silicon or tin group is what cleanly drives the reaction forward.
Okay.
And a related, but equally powerful application involves alkynyl silanes and stananes. Similar to their allylic counterparts, these compounds are fantastic for delivering vinyl groups. That's a carbon-carbon double bond directly attached to the metal.
Like R2CCH metal.
Precisely. Delivering those to electrophiles. Again, this occurs with demetallation. The net effect here is that the silyl or stanol group is cleanly substituted for something new, providing an efficient way to introduce double bonds into complex molecules with great control over their placement and configuration, which is, a big deal in molecular design.
That's a great overview of the fundamental differences. It sounds like each element has its own signature move in this molecular dance. Now, let's dive deeper into boron compounds. How do we actually make these organoboranes in the first place before we put them to work building carbon chains?
Right, good question. The most widely used and versatile route to creating organoboranes is through a reaction called hydroboration.
Hydroboration, adding BH across a double bond.
Exactly. It involves the addition of a boron-hydrogen bond across a carbon-carbon double bond. This is an incredibly powerful and efficient method for making both alkyl and alkynyl boranes, where the boron is attached to a saturated carbon chain or directly to a carbon within a double bond, respectively.
Okay, that covers alkyl and alkynyl, but what about others like aryl or allylic?
Yeah, for others like aryl boranes, where boron is attached to an aromatic ring, or specific allylic and benzyl boranes, hydroboration isn't typically the go-to method. For those, the most general route involves reacting a powerful organometallic compound, something like a Grignard reagent, RMGX, or an organolithium reagent, RLI, which are strong carbon nucleophiles.
The real workhorses?
Reacting those with a boron halide, like BF3, or an alkoxy-boron derivative, like BOR3. These reactions allow chemists to precisely link different carbon frameworks to boron, acting as the starting point for more complex structures.
So you swap a halogen or an alkoxy group on boron for your desired carbon group using a Grignard or organolithium.
That's the core idea. For instance, you can react a Grignard with BF3 to make R3B, or use an organolithium with something like RBO-IPR2 to make unsymmetrical RBR-type compounds. Even organocopper reagents cuprates can react with things like 9-BBN. It's quite versatile.
And you mentioned alkoxy-boron compounds.
Yes. Beyond simple trialkylboranes, various alkoxy-boron compounds are absolutely crucial in synthesis. These are boron compounds where one or more oxygen atoms are also attached to the boron. Compounds with one alkoxy group are called boronates, like R2BOR.
Okay.
Those with two are boronates, like RBOR. And trialkoxyboron compounds are called borates, BOR3.
Boronates, boronates, borates.
Among these, the cyclic 5- and 6-membered boronate esters, like those derived from pinacol, the 132-dioxaborlanes, or from 133-propanedyl, the 133-dioxaborananes are incredibly common and versatile.
Why the cyclic ones?
Well, they tend to have enhanced stability, they're easier to handle, often crystalline solids, and they still have predictable reactivity. This makes them excellent user-friendly building blocks for a vast array of synthetic challenges.
Okay, so we've synthesized these various boron compounds. How do we then put them to use to actually build new carbon chains? What are the key reactions that allow us to extend our molecular structures, perhaps even by just one carbon at a time?
This leads us directly into what chemists call carbonylation and other one-carbon homologation reactions. Homologation, simply put, means extending a carbon chain, often by adding just one carbon atom.
Lengthening the chain by one carbon.
Precisely. Now, most organoboranes, meaning those with 3 organic groups attached to a single boron, R3b, aren't inherently supernucleophilic. They're not typically prone to directly attacking other molecules on their own. However, they are moderately reactive Lewis acids, meaning they can accept electron pairs.
Right, boron wants electrons.
Exactly. The real magic, and where the carbon-carbon bonds begin to form, happens when they interact with a Lewis base and form a tetracoordinate intermediate. In this intermediate, the boron atom temporarily gains a 4th bond and carries a formal negative charge. Think of it as B becoming B minus.
Okay, 4 bonds, negative charge on boron.
This negative charge on boron, coupled with the expanded coordination, significantly weakens the existing carbon-boron bonds. This weakening is the key that enables the efficient transfer of a carbon substituent, one of the R groups, along with its pair of electrons, to a new electron pore center. It's like the negative charge pushes the R group off.
The negative charge makes the CB bond easier to break and allows the R group to move.
Exactly. And a significant group of reactions following this pattern involves the reactions of organoboranes with carbon monoxide, CO, which itself acts as a Lewis base. Carbon monoxide forms a temporary bond with the organoborane's boron atom.
CO sticks to the boron.
Yep. In this temporary structure, the boron has that negative charge, and importantly, the carbon atom of the carbon monoxide molecule becomes highly electron poor, or electrophilic, ready to be attacked. This electron-deficient carbon of CO then becomes the target for the R groups, the alkyl groups, to migrate from the boron.
So the R groups jump from boron onto the CO carbon.
That's the essence of it. And this migration is incredibly versatile and can be precisely controlled to result in the transfer of 1, 2, or even all 3 of the boron substituents, depending on the reaction conditions.
Wow, okay. How do you control how many groups jump?
It's all about the conditions. For example, if you just heat the organoborane with carbon monoxide, say 125 degrees Celsius, all 3 organic groups can migrate from boron to carbon. After a simple oxidation step, usually with hydrogen peroxide and base, you end up with a tertiary alcohol. That's R3COH.
All 3 groups move, make a tertiary alcohol. Okay.
But the versatility doesn't stop there. If you conduct the same carbonylation reaction in the presence of water, the reaction stops after the migration of 2 groups from boron to carbon. Subsequent oxidation of this intermediate will then yield a ketone, R2CO.
2 groups move, add water, get a ketone.
Right. And if you're aiming for a primary alcohol, RCH2OH, meaning an alcohol where the hydroxyl group is on a carbon attached to only one other carbon.
Just one R group transferred.
Exactly. You can carry out the carbonylation in the presence of a mild reducing agent, like sodium borohydride or lithium borohydride. In this case, the product of the first migration step is immediately reduced before a second group can move, giving the primary alcohol after oxidation.
Okay, reducing agent stops it after one migration. That's clever. But what if your R groups on boron are different? Or if you only want one specific R group to migrate?
That's a great point. If you start with R3b, where all R groups are the same, it doesn't matter which one migrates. But if you have different groups, or if your R group is precious, you don't want to waste 2 equivalents. To make this primary alcohol process more efficient, chemists often use bulky boranes like 9-BBN, 9-borbicycle 3.3.1-9.
9-BBN. I've heard of that one. It's bulky, right?
Very bulky. When you make an alkyl derivative, say R9-BBN, and react it with CO and a reducing agent, the bulky bicyclic part of the 9-BBN is much less likely to migrate than your desired R group. So it preferentially directs the desired alkyl group transfer. This allows you to efficiently convert an alkene into a primary alcohol with 1 extra carbon, RCH-CH2, makes so RCH2CH2, CH2-2OH, or make aldehydes or other useful homologated products.
That's incredibly precise control just by tweaking the conditions and the boron region. So it's not just carbon monoxide that can induce these migrations, right? What other clever ways have chemists found to add just 1 carbon at a time?
You're absolutely right. The versatility extends beyond just CO. Several alternative procedures have been developed using other reagents to achieve similar 1-carbon homologations. One of the most generally applicable and powerful methods involves the use of cyanide ion, CFAA, along with trifluoroacetic anhydride, TFAA.
Cyanide and TFA, how does that work?
In this reaction, the organoborane first forms an adduct with a cyanide ion, R3BCN. The crucial migration of an alkyl group from boron to carbon is then induced by acylation of the nitrogen by TFAA. This makes the cyanide-carbon electrophilic, ready for the R group shift.
So TFAA triggers the migration.
Pretty much. After this migration, a simple oxidation and hydrolysis will yield a ketone, R2CO. This particular method has become a highly effective and widely used strategy for ketone synthesis in organic chemistry.
Another route to ketones.
Okay.
Any others?
Another useful region for introducing that single carbonyl carbon is dichloromethyl methyl ether, Cl2CHOCH3. When this compound is used in the presence of a specific hindered alkoxide base, it gets deprotonated and acts as a nucleophile that attacks the electron-deficient boron.
Okay, it adds to boron.
Once this adduct forms, a rearrangement quickly follows, where two boron substituents migrate to the carbon originating from the ether. Again, subsequent oxidation of the intermediate yields a ketone, R2CO.
Two groups migrate again, like with CO and water.
Correct. What's especially useful about these methods, particularly the cyanide TFAA or the dichloromethyl methyl ether route, especially when combined with special bulky boranes, like the sexyl borane.
The sexyl borane, another bulky one.
Yeah, even bulkier than 9-BBN in some ways.
Yeah.
Using the sexyl borane allows chemists to build unsymmetrical ketones, where the two carbon chains attached to the carbonyl are different, RCOR. You can add one R group to the sexyl borane via hydroboration, then add a different R group using an organolithium or Grignard, and then do the carbonylation or cyanide reaction.
Ah, sequential addition.
Exactly.
Yeah.
The bulky thexyl group ensures that it doesn't migrate, making only the desired R and R carbon chains migrate, enabling very precise step-by-step construction of unsymmetrical ketones. You can even start with reagents like IPCBCl2, ispinocamphyl boron dichloride, do sequential reductions and hydroborations with two different alkenes, and then use these migration methods to build complex unsymmetrical ketones with chirality.
The control is just phenomenal. And you mentioned chirality. What's the impact on stereochemistry during these megadditions?
That's a critical point. The overall impact of these boron to carbon migrations is incredibly valuable for forming new carbon bonds. And a crucial feature is that they occur with retention of configuration of the migrating group.
Retention of configuration, so the 3D shape stays the same.
Precisely. This means that if you start with a chiral center, a carbon atom with 4 different groups attached, giving it a specific 3-dimensional orientation on your boron compound, that exact stereochemical orientation is preserved in your final product. The R group migrates with its stereochemistry intact.
Wow.
This retention of configuration is a huge deal because it opens wide the doors for enantioselective synthesis. This is the ability to selectively produce one specific mirror image form, an enantiomer, of a chiral molecule over its counterpart.
Which is vital for drugs, right?
Yeah.
Often only one mirror image works.
Absolutely critical for pharmaceuticals, where often only one enantiomer has the desired biological activity, and the other might be inactive or even harmful. For example, using specialized chiral boranes like monoisopenocamphyl borane, IPCBH2, which comes from naturally occurring alpha pine and is available in high enantiomeric purity.
Okay, a chiral borane reagent.
You can hydroborate a non-chiral alkene to create a new chiral center on the boron atom with high selectivity. Then you introduce a second alkyl group, maybe remove the chiral pine part, and perform one of these carbonylation procedures. This yields a chiral ketone, often with good enantiomeric excess, maybe 60–90% niches.
So you use the chiral borane to set the initial stereocenter, and the migration preserves it.
Exactly. And there are even more refined procedures using cyclic boronates in the thexyl groups that can achieve even higher enantiomeric purity. Chemists have made complex chiral cyclic ketones, like trans-1-decalone, with over 99% enantiomeric excess using these strategies. It's truly powerful for building specific 3D structures.
Wow, the precision you just described is astounding. It's like molecular origami where every fold matters. What other tricks does boron have up its sleeve beyond just adding carbons to make these complex structures? Can it help us build carbon chains and also control the location and geometry of double bonds?
Indeed, it's a very precise art. Beyond direct carbonylation, boron also excels in homologation via alpha halonolates. This is another powerful way to extend a carbon chain using organoboranes, but it involves starting with alpha halocarbonyl compounds.
Alpha halo. So a halogen next to a CO, like ethyl bromoacetate.
Exactly, things like ethyl bromoacetate or alpha haloketones or even alpha halonitriles. When these react with organoboranes, R3b, in the presence of a base, the base pulls off a proton to form an enolate, an electron-rich carbon, next to the carbonyl.
Okay, the enolate forms.
This electron-rich enolate carbon then adds to the electron-deficient boron in the organoborane, again forming that crucial tetracoordinate intermediate R3bCx-CO.
The boron gets attacked again.
Right. The key step then is a migration of an alkyl group, R, from boron to the alpha carbon, which occurs simultaneously with the Halley ion X leaving. It's an intramolecular SN2-like displacement on boron.
So the R group moves and kicks out the halogen?
Precisely. And just like in the carbonylation reactions, retention of configuration of the migrating R group is consistently observed here, maintaining any existing chirality. This gives you a homologated ester, ketone, or nitrile. There's a similar reaction using alpha-diazo esters or ketones, where molecular nitrogen N2 is the leaving group instead of a halide.
Okay, another way to extend chains while keeping chirality. Very neat.
And this ability extends to controlling the geometry of double bonds, leading us to stereoselective alkene synthesis for both Z or cis and E or trans alkanesins. Achieving precise control over double bond geometry is critical because Z and E isomers can have vastly different properties and biological activities.
Right, cis versus trans can make a huge difference. How does boron help there?
Well, chemists have developed several clever methods. For making Z-alkanes, cis, one common approach is to treat alkyl dialkylanes, R2bCHCHR, with iodine in the presence of a base like sodium methoxide.
Iodine and base.
Yes. The iodine attacks the double bond carbon, and then the base induces an anti-elimination of the boron group and an iodine atom, leading specifically to the Z-alkane. The geometry is set because of that specific anti-elimination mechanism where the leaving groups depart from opposite faces of the molecule.
Anti-elimination gives Z. Okay, what about E-alkanes?
For E-alkanes trans, a different strategy is needed. One way involves hydroboration of a bromoyl alkene. This gives you an alpha-bromoyl alkenyl borane.
Boron and bromine on the same double bond carbon.
Yes, geminal arrangement. Then treatment with sodium methoxide induces a boron to carbon migration of an R group, kicking out the bromide. Protonolysis, adding acid of the resulting intermediate, then gives the A-alkene.
So migration again, but starting from an alkene this time.
Right. And again, the caxyl-borane derivatives can be useful here because the sexyl group won't migrate, ensuring your desired R group moves. There are variations, but the core idea is controlled migration and elimination to set the E geometry. Chemists can even make complex dry-substituted alkenes with specific geometry using related methods.
It seems boron is fantastic for making specific double bond geometries. Can it also make alkenes?
It can contribute there, too. Adducts formed between terminal alkenes and boranes, when reacted with iodine, can undergo electrophilic attack by iodine at the triple bond. This is followed by alkyl group migration from boron and elimination of dialkyliodoboron, yielding an alkylated alkene, RCCR. So yes, another tool for the toolbox.
That's a fantastic overview of alkene and alkene synthesis using boron. Now, shifting gears a bit, how do allylic boron compounds specifically behave when they encounter aldehydes and ketones? Are we talking about similar controlled additions there, perhaps for building alcohol structures?
Indeed, this is a particularly important and powerful application. The nucleophilic addition of allylic groups from boron compounds. These reactions are crucial for efficiently forming allylic carbonyls, which are alcohols with a double bond right next door in the beta-gamma position, to the carbon bearing the hydroxyl group, HCC-COH.
Allylic carbonyls. Okay, so adding an allyl group to a CO.
Exactly. The mechanism is quite elegant. Allylic boranes, like 9-alanine BBN for instance, initiate the reaction by coordinating their Lewis acidic boron to the carbonyl oxygen of the aldehyde or ketone.
Boron sticks to oxygen again?
Yep, that Lewis acid-base interaction. This has a dual effect. It makes the carbonyl carbon significantly more electron-hungry, more attractive to the electron-rich allyl group, and simultaneously weakens the carbon-boron bond to the allyl group, making it ready to transfer.
Activates both partners.
Right. What follows is the formation of that characteristic cyclic transition state, typically a temporary six-membered chair-like structure. You might hear it called a Zimmermann-Traxler transition state.
Okay, that organized ring structure again.
Yes. During this, the new carbon-carbon bond forms precisely at the gamma carbon of the allyl group, the one furthest from the boron. And simultaneously, the double bond within the allyl system shifts its position from CCCB to CCC.
So it adds at the end of the allyl group and the double bond moves.
Exactly. This cyclic mechanism is absolutely key to understanding the stereospecificity of these additions. It accurately predicts that the reaction will be stereospecific with respect to the geometry of the double bond in the allylic group.
Meaning E vs Z in the starting material matters.
Hugely. Experiments confirm this. For instance, if you start with an E-allylic borane, like E2-butyl boronate, it consistently gives you the carbonyl with anti-stereochemistry at the newly formed chiral centers.
E gives anti.
Conversely, if you use the Z-allylic borane, Z2-butyl boronate, it exclusively leads to the syn product.
Z gives syn. That's incredibly predictable.
It is. This predictability arises because, in that chair-like cyclic transition state, the larger substituent on the aldehyde preferentially occupies an unhindered equatorial position, which then dictates the final relative configuration, syn or anti, of the product.
Amazing control based on that temporary ring structure. What about using chiral boranes?
That's where it gets really powerful for asymmetric synthesis. This high level of control is further refined when dealing with enantiomerically pure allylic boranes. For example, using a chiral borane reagent derived from isopenocamphyl groups like IPC2B allyl allows chemists to react with simple aldehydes and produce chiral allylic carbonyls with very high enantiomeric purity, often over 90% E.
So you can make predominantly one mirror image.
Yes, and this is a clear example of reagent-controlled stereoselectivity. The configuration of the product is primarily determined by the chirality of the borane reagent itself, rather than the substrate.
The reagent dictates the outcome.
Precisely. And since both mirror image forms of these chiral boranes, derived from plus or alpha pine, are often readily available, chemists have the flexibility to prepare either an enantiomer of a desired product from a given aldehyde, which is immensely valuable in drug synthesis.
Yeah.
Interestingly, purifying these boranes, removing magnesium salts for instance, makes them react even faster and sometimes with even higher selectivity.
Purification helps too. Are there other types of chiral allyl boron reagents?
Oh yes, another extensively developed and incredibly powerful group of lilac boron reagents are those derived from tartrates. Disopropyl tartrate, for example.
Tartrates, like from wine.
Related. These tartrate-derived reagents achieve very high stereoselectivity, often leading to either anti or syn products with great precision, depending on how they're made. Their enantioselectivity is also very good, typically 80-90% E.
So good control over relative and absolute stereochemistry.
Exactly. They're especially useful for synthesizing complex polyketide natural products, which often feature intricate arrays of alternating methyl and oxygen substituents along their carbon backbone structures that are very challenging to make selectively.
Why are they so good for those?
The key to their exceptional enantioselectivity lies in the precise interaction between the aldehyde and the tartrate part of the reagent within that critical cyclic transition state. The tartrate ligand essentially creates a chiral pocket that locks the aldehyde into a specific orientation, leading to the observed high selectivity.
Like a chiral glove guiding the reaction.
That's a good analogy.
Yeah.
And the scope of allycollaboration has also seen exciting expansion through the discovery that it can be catalyzed by certain Lewis acids, notably scandium triflate.
Catalytic allycollaboration. Does that change things?
What's remarkable is that the catalyzed reaction maintains the same high diastereoselectivity as the uncatalyzed version, which strongly indicates that it still proceeds through that predictable cyclic transition state. But being catalytic means you need less of the boron reagent, or you can use less reactive boronates.
Makes it more practical, maybe?
Yes, and it has even made reactions of certain functionalized boronates possible, leading to specialized products like alpha-methylene lactones with high stereoselectivity. Furthermore, chiral catalysts based on chiral diols have been developed that can induce impressively high enantioselectivity, 90-95% EE, opening up new avenues for targeted chiral synthesis without needing a stoichiometric chiral borane.
Wow, catalytic and enantioselective.
These reactions are not just theoretical. They've been successfully applied in the complex multi-stage syntheses of intricate natural products like balinol, demonstrating their real-world impact. There are even variations using chlorosubstituted boranes for making vinyl epoxides or stable allyl tetrafluoroborates. And even alkynyl boranes can add to aldehydes. It's a very rich area.
That's a truly comprehensive look at organoboron chemistry. It's clear that boron offers incredible precision and versatility, almost like a master sculptor of molecules. Now let's shift gears to silicon. How does it compare to boron in building carbon frameworks, and where do its strengths lie?
Right. Moving on to silicon. Silicon, unlike boron, is quite unique in its electronegativity, being very similar to carbon.
Similar electronegativity, so the C-side bond isn't very polar.
Exactly. It's largely covalent. This similarity results in a carbon-silicon bond that is remarkably strong and stable, much stronger than Cb or CSN.
Strong and stable.
Yeah.
What does that mean for synthesis?
Well, this inherent stability means that many of the existing tools and transformations in organic chemistry can be directly applied to modify organosilanes after the silicon group is introduced. You can do reactions elsewhere in the molecule without worrying too much about the C-side bond breaking unexpectedly. It gives chemists a broad range of options for further elaboration.
So you can build up complexity around the silicon group. How are organosilanes typically made, given their different properties compared to boron?
There are two main routes, primarily. The first is nucleophilic displacement, similar in concept to how some boranes are made. This involves using powerful organometallic reagents like Grignard reagents or organolithium compounds to displace a halogen atom from a silicon halide, like the very common trimethylsilicylide, Me3-cell.
RMGX plus methylacyl gives R-symmetry, direct and simple.
Very direct and efficient way to introduce a silyl group, especially simple ones like trimethylsil. The second major route is hydrosylation.
Analogous to hydroboration, adding Psi-H across a multiple bond.
Exactly. It's the addition of silanes compounds containing a silicon-hydrogen bond across carbon multiple bonds, meaning alkenes and alkanes. Unlike hydroboration, which often occurs spontaneously, hydrosylation typically requires a catalyst, often a transition metal complex like hexachloroplatinic acid, H2PtCl6, or complexes of rhodium, ruthenium, or palladium.
Transition metal catalysts. Does the catalyst choice matter?
Oh, absolutely. The specific catalyst chosen can dramatically influence the outcome. It can determine whether the silicon and hydrogen add to the same side, syn addition, or opposite sides, anti-addition, of the double or triple bond. It dictates regioselectivity where the silicon ends up, and it strongly influences the resulting geometry, E or Z, of the double bond formed from alkenes.
So lots of control possible via the catalyst.
Definitely. For instance, some Lewis acid catalysts give anti-addition to alkynes, yielding Z-alkylsilanes. Rhodium catalysts often give E-alkylsilanes from terminal alkanes. Ruthenium can give Z-vinylsilanes. Wilkinson's catalyst, fascinatingly, shows stereoselectivity dependent on the order of mixing reactants.
Order of mixing matters, seriously.
Add the alkene to catalyst plus selene, you get the Z isomer. Add the selene to alkene plus catalyst, you get the E isomer. Subtle effects, big difference. There are also ways to make alkanosilanes related to the Peterson olefination, often involving elimination steps, which can also be controlled to give E or Z products.
That's a lot of ways to get silicon onto a carbon chain with precise control. So once we have these organosilicon compounds, what are the general rules for how they participate in carbon bond-forming reactions? What's the overarching pattern of their reactivity?
That's a crucial question. Unlike, say, organolithium or Grignard reagents, simple alkyl samines, where the silicon is attached to a saturated carbon chain, aren't very nucleophilic. As we said, the C-side bond is largely covalent, strong, and doesn't have high-energy electrons readily available for donation.
So just like boron, the action isn't with simple alkyl groups.
Primarily, no. Most of the truly valuable synthetic procedures based on organosilanes involve either alkanol, vinyl, or allylic silicon substituents. These double bonds introduce a special kind of reactivity that simple alkyl chains lack.
Okay, alkanol and allylic silanes are the key players. What's their main reaction pattern?
The dominant reactivity pattern for both alkanol and allylic silanes involves an initial electrophilic attack at the carbon-carbon double bond, followed by a process called disilyzation, where the silicon group cleanly leaves.
Attack, then silicon leaves. Demetallation again, essentially.
Exactly. For allylic silanes, the incoming electrophile, E+, typically attacks the gamma carbon, the carbon furthest from the silicon within the allyl system. E+ adds to CCCCS.
Okay.
This attack results in the loss of the silicon substituent and a characteristic shift of the double bond, giving ECCC.
Okay, attack at the end, double bond shifts, silicon leaves. Why does it attack there?
The crucial underlying influence on this reactivity pattern in both cases is what's known as the beta-silicon effect.
Beta-silicon effect. Okay, what's that?
Imagine a carbon atom developing a positive charge, a carbocation, right next door to a carbon atom that's bonded to silicon. That's the beta position relative to silicon. Silicon has a remarkable ability to stabilize this positive charge.
It helps the positive charge.
It's like having a little electronic cushion right where you need it. This stabilization is primarily attributed to a phenomenon called hyperconjugation. The electrons in the carbon-silicon sigma bond can overlap with the empty orbital of the carbocation, effectively spreading out that positive charge and making the intermediate more stable.
So the C-side bond electrons help stabilize the charge on the next carbon over.
Exactly. This is why if an electrophile attacks an allylic silane at that gamma carbon, it creates a positive charge at the beta carbon, which is nicely stabilized by the silicon. This stabilization drives the reaction forward and dictates the regiochemistry. Similarly, for alkanylsilanes, attack at the alpha carbon gives a beta carbocation.
Makes sense. What kind of reaction conditions are needed?
As for reaction conditions, most of these carbon bond-forming reactions of alkynyl and allylic silanes require strong electron-poor partners, strong electrophiles like activated carbonyls, iminium ions, or silyl halides. And they very often involve the use of Lewis acid catalysts to activate the electrophile and facilitate the desilylation step.
Lewis acids again.
Often, yes. Though there is an alternative pathway, activating allylic silanes with fluoride ion, like TBAF, tetrabutyl ammonium fluoride. Fluoride has a very high affinity for silicon.
Silicon loves fluoride.
It really does. Fluoride adds to silicon, forming a hypervalent anion, a 5-coordinate silicate species. This silicate is much more nucleophilic than the neutral silane, allowing direct transfer of an allylic anion without needing a Lewis acid. That opens up different reaction possibilities.
Fascinating how the silicon's inherent properties dictate the entire reaction pathway. Let's talk about a specific and widely known application: additions to aldehydes and ketones. This is often referred to as the Saccharine reaction, correct?
Precisely. The Saccharine reaction is indeed the widely recognized name for the Lewis acid-catalyzed addition of allylic silanes to carbonyl compounds like aldehydes and ketones. It's a cornerstone reaction in organic synthesis.
Okay, Saccharine reaction. Allyl Si plus CO with Lewis acid. What catalysts are used?
A variety of Lewis acids can promote this reaction. The originals were often strong ones like titanium tetrachloride, TDL4, or boron trifluoride etherate, BF3.0ET2. Others like indium chloride, scandium triflate, or even super strong silylating reagents can also work. These catalysts work primarily by coordinating to the carbonyl oxygen, activating the carbonyl group, making it more electrophilic and ready for attack by the allylic silane. Then a nucleophile, maybe from the catalyst, counterion, or solvent, helps kick off the silicon in the desilylation step.
Right. Now, you mentioned allylic boranes react via a cyclic transition state. What about allylic silyls here?
That's a key distinction. Unlike allylic boranes, which typically react via a tight 6-membered cyclic transition state, allylic silyls usually don't. Why? Because silicon possesses very little Lewis acid character itself. It doesn't readily coordinate directly to the carbonyl oxygen to close that ring.
So no inherent Lewis acidity means no easy ring formation.
Generally, yes. Instead, the stereochemistry of allylic silane additions in the Saccharine reaction is consistent with a more open acyclic transition state.
Acyclic? More floppy. Does that affect the outcome?
It does. This difference in mechanism leads to different stereochemical outcomes compared to boron. For example, if you start with an E2-butanol, trimethylsilane, it generally gives you almost exclusively the syn product upon reaction with an aldehyde.
E-silane gives syn product. Interesting. E-borane gave anti.
Exactly. Different mechanism, different outcome. The Z isomer of the silane is less selective, but also tends to favor the syn product. Computational models suggest specific acyclic arrangements, maybe anticyclonal, are preferred over others. There might be some subtle electrostatic interactions, perhaps between fluorine from BF3 and the silicon, giving it a tiny bit of cyclic character even in an open TS, but it's fundamentally different from the boron case.
Okay, mostly acyclic. What about chiral aldehydes?
When you introduce chiral aldehydes, meaning aldehydes that already have a specific three-dimensional orientation, there's usually a degree of diastereoselectivity that often follows predictable models of how the nucleophile approaches, like the Felkinam model. But interestingly, some aldehydes with specific oxygen substituents like alpha or beta benzyloxy groups, when reacted with allylic silanes in the presence of certain Lewis acids like tin tetrachloride, SNCl4, can show very high chelation control.
Chelation again, the Lewis acid bridging oxygens.
Yes. The SNCl4 can form a stable temporary 5 or 6-membered ring involving the aldehyde's carbonyl oxygen and the nearby benzyloxy oxygen. This locks the aldehyde into a specific conformation, guiding the incoming allylic silane to a specific face and leading to high stereoselectivity, often overriding the simple Felkinam preference.
So Lewis acid choice can switch between chelation and non-chelation control.
Absolutely. It's another layer of control. These reactions can also happen intramolecularly, where the allylic silane and the carbonyl are in the same molecule, leading to ring formation with often good stereo control.
What about making these additions enantioselective, using chiral catalysts?
That's been a tougher challenge for the standard Saccharide reaction compared to ally alburation, partly because of the acyclic nature. However, there's been progress with specific types of silanes. For instance, allylic trichlorosilanes, allyl-saccharide are particularly promising.
Trichlorosilyls, 6Cl3 instead of some E3. Why are they special?
They are more reactive, and importantly, they seem to react with aldehydes, often in coordinating solvents like DMF, to yield homoallylic alcohols with high stereoselectivity. These reactions are believed to proceed through a more organized cyclic transition state, possibly involving a temporary hexacoordinate silicon intermediate, silicon with 6 bonds.
Ah, the extra chlorines make silicon more Lewis acidic, maybe helping form a ring.
That's the thinking. Silicon can expand its octet more readily with electronegative groups attached. This heightened reactivity and control make them very attractive. Furthermore, sophisticated chiral catalysts, like chiral phosphoramides or axially chiral bipyridines, have been developed that can induce impressively high enantioselectivity, like 94-98 precision, EE, with these allyl trichlorosilines, allowing chemists to create specific mirror image products with great precision.
So trichlorosilines plus chiral catalysts are a good combo for enantioselectivity.
Yes, and allylic trifluorosilanes, LSF3, also leverage the ability of silicon to temporarily expand its bonding to a hexacoordinate state. This presents a fantastic opportunity for chelation control. For instance, alpha-hydroxyketones can react with these trifluorosilanes to give syndials with high selectivity. This is incredibly powerful for constructing compounds with multiple contiguous chiral centers, like those found in complex natural products like zincoforin. It allows for building up intricate molecular architecture with very high control over three-dimensional shape.
Trifluorosilanes for chelation control. Got it. And you mentioned fluoride activation earlier.
Right, the fluoride ion activation. Adding fluoride, like TBAF, can powerfully enhance the nucleophilicity of allylic silanes by forming those hypervalent silicates. This allows additions to less reactive electrophiles like ketones or facilitates useful ring closures, often without needing a strong Lewis acid. There are even catalytic versions using fluoride sources with copper or silver catalysts combined with chiral ligands like BNAP to achieve high enantioselectivity.
That's a deep dive into silicon's reactivity with carbonyls. What about those tricky nitrogen-containing electrophiles, the iminium ions? How do allylic and alkynyl silanes handle those?
The iminium ions are indeed very reactive electrophiles, and both alkynyl and allylic silanes engage readily with them.
Useful for making nitrogen rings.
Exactly. This reactivity is particularly useful for forming nitrogen-containing rings, which are prevalent in many natural products and pharmaceuticals. These reactions often involve generating the iminium ions right in the reaction mixture, in situ, typically from amines and formaldehyde or other aldehydes. For example, a simple chain-like amine containing an allyl could cyclize to form a nitrogen-containing ring like a piperidone.
Neat cyclizations.
Even more reactive are N-acylaminium ions. These are often generated from amides or amides after partial reduction or other activation steps. Once formed, they readily react, often intramolecularly, with both allylic and vinylsilanes tethered to the molecule, creating complex, polycyclic nitrogen-containing structures. This is a very powerful strategy for building the intricate frameworks found in alkaloids and other nitrogen heterocyclic compounds.
Okay, iminium ions are good partners too. And acylation reactions. That sounds like putting a carbonyl group directly onto a silicon-containing molecule, is that right?
Yes, that's exactly what it is. Acylation reactions involve the direct introduction of an acyl group RCO onto a molecule replacing the silicon. Alkynyl silanes, vinylsilanes for instance, react with acid chlorides, RCOCl, usually catalyzed by Lewis acids like aluminum chloride, LCl3, or tin tetrachloride, SnCl4, to form alpha-beta unsaturated ketones.
Vinylsilane plus acid chloride gives an enol.
Correct. These are molecules with a double bond right next to a ketone, very important building blocks. Titanium tetrachloride can even induce reactions with dichloramethyl ether to create alpha-beta unsaturated aldehydes.
Okay. What about allylic silanes?
Allylic silanes react with acyl halides under similar Lewis acid catalyzed conditions, leading to beta-gamma unsaturated ketones, RCOCH2CHCH2.
Acylation happens at the gamma carbon again.
Yes, with the usual double bond shift. The mechanism for these acylation reactions likely proceeds via acylium ions, RCO+, which are highly reactive, positively charged carbonyl species generated from the acid chloride and Lewis acid, acting as the electrophiles. These reactions allow chemists to efficiently incorporate carbonyl groups and design new molecular skeletons.
Seems very versatile. Finally, for silicon, how do allylic silanes perform in conjugate addition reactions? This is where they add to a double bond conjugated with a carbonyl rather than directly to the carbonyl itself, right?
It's precisely correct. Conjugate addition, or 1,4 addition, is another incredibly powerful application of allylic silanes, typically involving alpha-beta unsaturated ketones or esters, anonines, or enos, and once again, usually facilitated by Lewis acids like TCl4.
So instead of attacking the CO carbon 1 and 2 addition, it attacks the beta carbon.
Exactly. The allylic group adds to the beta carbon of the conjugated system, and the electron density shifts, ultimately protonating the enolate intermediate at the alpha position. The net result is addition across the CSE double bond.
Okay. What about stereoselectivity here?
The mechanism and stereoselectivity in these conjugate additions are quite intriguing. The allylic group approaches the conjugated system from a trajectory that aligns optimally with the molecule's lowest unoccupied molecular orbital, LMAO, often leading to predictable stereochemical outcomes, especially in cyclic systems where approach is dictated by steric hindrance.
So it adds to the less hindered phase, usually.
Often, yes. For cyclic systems, things can get more complex. Specific Lewis acids can lead to fascinating chelation control, just like in the 12-2 additions. For instance, the E form of an enol might react via an open transition state to give a syn product relative to an existing stereocenter, while its Z isomer might react through a chelated pathway using TCl4 to give an antiproduct. This highlights how subtle changes in geometry or catalyst choice can dramatically alter the stereochemical pathway.
Chelation can control 134 addition too?
It can. Fluoride can also induce these conjugate additions, sometimes even with esters and amides. These reactions are broadly useful, allowing for the formation of complex structures, even creating notoriously difficult structures like quaternary carbons, carbon atoms bonded to 4 other carbon atoms, which are common but challenging motifs.
That wraps up silicon, and it's clear it brings a whole different kind of control and selectivity to the table compared to boron. Now, let's explore tin. What makes organotin compounds special for carbon bond formation, and how do they generally compare to their silicon and boron counterparts?
Right, on to tin, the last of our trio. Organotin compounds, or organostanins, are truly special for carbon bond formation because they're generally more reactive than their silicon counterparts.
More reactive than silicon, why is that?
This increased reactivity stems from 2 key factors. First, the carbon-tin bond, CSN, has a greater partial negative charge on the carbon atom compared to CSI. It's more polar, making the carbon more nucleophilic and electron donating.
More delta minus on carbon.
Exactly. And second, crucially, the carbon-tin bond is inherently weaker than the carbon-silicon bond. It requires less energy to break.
More polar and weaker bond. So easier to get the carbon group to react.
Precisely. Both of these properties contribute to tin's enhanced ability to transfer carbon groups more readily, often under milder conditions than silicon requires.
Okay, higher reactivity. How are organostanins typically synthesized? Is it similar to the other elements?
There are indeed some parallels, but also distinct differences reflecting tin's unique properties. One important route is hydrostanylation, adding an SNH bond across a multiple bond, analogous to hydrosilylation.
Hydrostanylation. Does it need catalysts too?
It can be done in several ways. Sometimes it proceeds via radical chain processes, often initiated by radical initiators like AIBN. This is quite different from typical hydrosylation or hydroboration. Alternatively, it can be catalyzed by Lewis acids like zirconium tetrachloride, ZrCl4, which can give ZL-conylsanins, or by palladium catalysts. Palladium-catalyzed reactions usually give syn addition, where the tin and hydrogen add to the same side of a double or triple bond.
Radicals, Lewis acids, or palladium. Lots of options for hydrostanylation.
Yes. Another common approach involves displacement reactions. Allylic stanins can be made from allylic halides or compounds with similar leaguing groups, like acetates or phosphates, by displacing them with strong tin nucleophiles like lithium trialkylsilyl, LIS-NR3, or using palladium catalysis for the acetate-phosphate displacements.
Similar to making olefinlanes.
Quite similar concept. For aromatic tin compounds, arylstanins, the most common route involves reacting an aryl organometallic reagent, like an arylithium or Grignard, with a trialkylton halide, R3SNCl or R3SNBr.
Standard organometallic coupling.
Exactly. There are also some multi-step methods to make specific types, like terminal alkylstanins from aldehydes, and trialkylsilyl R3SN, generated by deprotonating R3SNH or via other routes, are potent nucleophiles themselves. They can add to things like carbonyls or aminium intermediates to make alpha-alkoxy or alpha-amino-alkyl stanins.
Lots of ways to make them. So, given their higher reactivity compared to silicon, how do organokin compounds participate in carbon bond-forming reactions? What are the key patterns, and what kind of control can we expect?
The most synthetically useful procedures with organotin compounds involve electrophilic attack on alkynyl and allylic stanins, similar in principle to silanes, but often with that enhanced reactivity due to the weaker, more polar carbon-tin bond.
Okay, let's focus on the allylic ones again. Allylic trialkylstanins. How do they react with aldehydes?
Right, allylic trialkylstanins. While they're generally more reactive than silanes, they're typically not reactive enough to add directly to simple aldehydes at room temperature. However, heating the reaction can induce addition. More practically, using Lewis acid catalysts like boron trifluoride, BF3, allows the reactions to proceed under much milder conditions.
Lewis acids needed again, usually.
Usually, yes, and the reaction proceeds with the characteristic allylic transposition, double bond shift, and distannylation, loss of tin.
Same pattern as silanes. Attack at gamma, double bond shifts, metal leaves. What about stereoselectivity? Is it like silicon's cyclic mechanism?
This has been a major area of study, and it's complex. A remarkable finding is that with certain aldehydes, like benzaldehyde, BF3 catalyzed addition of two butyl stanins, both E and Z isomers, often gives almost exclusively the syn isomer.
Syn isomer, regardless of starting E or Z geometry.
Often, yes. This is quite remarkable stereoconvergence. It suggests that either the E and Z stanins rapidly interconvert under the reaction conditions before adding, or that the reaction proceeds through a common intermediate or transition state that dictates the final syn stereochemistry, essentially erasing the memory of the starting material's geometry.
Stereoconvergence. The reaction funneling to one outcome. Why syn?
It's thought that the reaction appears to favor an acyclic synclinal transition state, which is a specific arrangement of atoms that leads to the observed syn product, possibly due to minimizing certain steric interactions, even though it looks a bit crowded. It's different from the anti-preference often seen with boranes.
Okay, often stereoconvergent to syn with simple Lewis acids. What about chiral aldehydes?
When you use chiral aldehydes, the reagent approach generally follows a Felkin model, predicting approach from the less hindered face relative to the existing chiral center. This preference can be either reinforced or opposed by the effect of other stereocenters already present in the aldehyde.
Standard chiral aldehyde behavior. Can we get chelation control with tin?
Yes, absolutely. With aldehydes where chelation can occur, like an alpha-benzyloxyaldehyde, specific Lewis acids like magnesium bromide, MgBr2, or again tin tetrachloride, SnCl4, can lead to a dominance of the syn stereoisomer. They form that temporary bridge with the oxygen atoms, locking the conformation and guiding the reaction precisely. However, introducing just one additional methyl group nearby can sometimes completely flip the selectivity to anti, indicating a very subtle and delicate balance of steric and electronic factors within these chelated structures.
Wow, very sensitive to structure. What about other types of tin reagents?
Next, we have allylic halostamins, like allysilton trichloride, LaSNCl3. These are particularly fascinating.
Halogens on tin, like the trichlorosilanes.
Similar idea. They're fascinating because the reagent itself acts as both a Lewis acid, the SnCl3 part is Lewis acidic, activating the carbonyl, and the nucleophilic allyl source.
Bifunctional. Does that change the mechanism?
It's believed that reactions involving these halostanins often proceed through cyclic transition states, much like allylic boranes, which can explain higher levels of stereocontrol compared to the R3SN Lewis acid systems. These reagents can even be generated right in the reaction mixture in situ from simple starting materials like allylic halides and tin metal or tin halides like SnCl2.
Cyclic TS, so maybe more like boron in terms of stereospecificity.
Sometimes, but it's complex. For example, SnCl2 promoted reactions often give antiproducts, but they can still be stereoconvergent for E and Z starting materials, suggesting maybe isomerization happens before the addition step.
Okay, halostanas add another layer. You mentioned transmetallation earlier with silicon. Does that happen with tin?
Yes, transmetallation is a very important concept with tin reagents too, especially with strong Lewis acids like titanium tetrachloride, TCl4. The reaction may involve a prior transmetallation step where the allylic stanin first transfers its allyl group to the titanium, forming an allylic titanium intermediate, allyl TiCl3, which then reacts with the aldehyde.
Tin gives the allyl group to titanium first.
Potentially, yes. This introduces additional factors into the stereoselectivity analysis, as the stereochemistry of both the transmetallation step and the subsequent addition step needs to be considered. Both steps could potentially proceed with retention or inversion.
Makes it much harder to predict.
It can. For example, when T4 is used as the catalyst, sometimes the order of addition of the reagents can dictate whether you get predominantly a syn or anti-product. Adding the aldehyde to a preformed mixture of STANN and TCl4 might give one outcome, while adding TCl4 to the STANN and aldehyde might give another.
Order of addition matters again.
It can, suggesting different intermediates are involved depending on how you mix things. Interestingly, with some Lewis acids, like indium chloride and Cl3 in certain solvents, the process might involve inversion at the transmetallation step and inversion at the addition step, leading to an overall retention of the allylic stereochemistry from the starting material to the product. It's like two wrongs making a right, stereochemically speaking.
Mind-bending. Okay, what about functionalized tin reagents?
Gamma-oxygen-substituted STANNs are particularly useful synthetically, especially for building polyoxygenated carbon chains found in sugars and polyketides. For instance, E-gamma-alkoxy, or silyloxyallylic STANNs, react with aldehydes, often mediated by BF3, to give primarily syn adducts.
Oxygenated STANNs give syn.
Often, yes. And when these are combined with alpha-substituted chiral aldehydes, chemists can sometimes achieve matched and mismatched combinations. The inherent preference of the STANN and the aldehyde might align to give very high selectivity, matched, or they might oppose each other, leading to lower selectivity, mismatched. This allows for extremely precise construction of multiple chiral centers along a chain by choosing the right combination. Chelation control with SNCl4 can also play a big role here, sometimes overriding the inherent preferences.
So you can play the reagents off each other. What about enantioselective additions with tin, catalysts again?
Yes. The field has seen significant advances in enantioselective additions of allylic STANNs. Sometimes the chirality already present in the STANN region itself, especially if there's an oxygen substituent nearby, can exert powerful control over the product's stereochemistry. Both substrate-controlled additions, where the aldehyde's chirality dominates, and reagent-controlled stereoselectivity, where the tin region's chirality dictates the product, are possible.
Okay.
Chemists have devised incredibly sophisticated strategies using sequential additions and controlling acyclic, chelation, and cyclic transition states to build complex targets, even constructing all 8 possible configurations of hexose sugars using these tin reagents. It demonstrates astounding control over complex molecular architecture.
Building all the sugars, that's impressive. Are there chiral catalysts for tin too?
Yes. Chiral catalysts have also been developed. For example, chiral bienol ligands combined with titanium can give good enantioselectivity, 85 and 95% AD in some allylations. Chiral binap ligands with silver fluoride, AGF, can also provide good enantioselectivity, often for antiproducts, and sometimes even showing that seroconvergence we talked about getting the same chiral product regardless of starting EZ geometry.
Silver and binap. Interesting.
And these allylic stannins don't just react with aldehydes. They also react readily with electrophilic intermediates generated from acetyls or dithioacetyls, usually activated by Lewis acids or other reagents, providing more ways to form CC bonds.
Acetyls too. One last variation. Alanyl stannins. What are they?
Alanyl stannins are a useful variation where the tin is attached to a carbon in an alene system, CCCCAZN. They have unique reactivity. They can be made in enantiomerically pure form and react with aldehydes under Lewis acid influence, often BF3. With branched aldehydes, they show a strong preference for the synadduct. Chelation control is also observed with alpha-benzyloxyaldehydes using MGBR2.
Alenes add complexity but also opportunity.
Exactly. And these alanyl stannins can even be transmetallated by SNCl4 to form related propergyl stannins, SNCC, which then react stereospecifically with aldehydes via cyclic transition states. So they offer yet another pathway to stereo-controlled synthesis.
That was an incredible tour through the detailed reactivity of organotin compounds. It truly underscores their power and the fine control they offer, even with the added complexity of transmetallation and stereoconvergence. So what does this all mean for us? We've covered a lot of ground with boron, silicon, and tin, each with its unique quirks and strengths. What are the overarching themes for predicting stereoselectivity in these carbon-carbon bond-forming reactions? How do we make sense of all these patterns?
This raises an important question, and it's essential to zoom out to the big picture because you're right, we've gone through a lot of detail. Despite the apparent complexity and the many subtle influences we've discussed, Lewis acid choice, chelation, substrate structure, reagent structure, EVSZ geometry, potential for equilibration.
Yeah, it feels like a lot to juggle.
It can seem that way. But these reactions generally fall into a few predictable patterns when it comes to stereoselectivity. Understanding these overarching themes allows chemists to design and predict reaction outcomes much more effectively, which is truly the art of synthesis. It's about seeing the forest despite all the trees.
Okay, what are these main patterns?
The first pattern involves reactions proceeding through monocyclic transition states with substrate control. This is the classic picture for many allylic borane reactions.
The Zimmermann-Traxler model you mentioned.
Exactly. Boron's inherent Lewis acidity promotes a tight, often chair-like temporary six-membered ring structure during the reaction. In these cases, the dominant factors dictating the stereochemistry are the intrinsic E or Z geometry of the allylic region itself and the conformational preferences of the reacting aldehyde, like the Falkenand preference for where substituents sit. It's largely about the inherent three-dimensional structure of the starting materials guiding the reaction through that very organized temporary ring. E gives anti, Z gives syn, generally.
Okay, pattern 1. Boron, cyclic TS. Highly predictable from starting geometry.
Pretty much. The second pattern involves reactions proceeding through open transition states. We see this exemplified in the Lewis acid-catalyzed additions of many allylic silanes, and also the trialkylsilyls when simple Lewis acids like BF3 are used.
The Saccharine reaction falls here mostly.
Yes. Here, because the Lewis acid character of silicon and tin is less pronounced, there isn't the same strong driving force for a tight cyclic transition state involving the metal. As a result, the degree of stereochemical control can be more variable, often only moderate. Steric factors in the more flexible, open transition state play a larger role, and interestingly, the E and Z isomers of the allylic reactant can behave quite differently, or even converge to the same product, as we saw with kin-giving syn products.
Pattern 2. Silicon, R3M, open TS, less predictable stereoconvergence possible.
That's a good summary. The third key pattern is reactions through chelated transition states. This becomes particularly important when aldehydes or ketones have oxygen atoms, or sometimes other heteroyl atoms, strategically placed at the alpha or beta position.
Like the alpha-benzyloxy aldehydes.
Precisely. These groups can form temporary bridges with certain Lewis acids, especially ones like MgBr2, ZnCl2, Tice4, SnCl4, effectively creating a rigid, temporary multi-ring cage around the reaction site. Chelation can also sometimes occur with substituents on the allylic reactant itself if it has appropriately placed oxygens.
Chelation locks things down.
It does. The overall stereoselectivity in these cases is often very high and predictable, governed by a delicate balance of steric and stereoelectronic effects within that tightly constrained chelated transition state. This mechanism offers a powerful and highly predictable way to control multiple chiral centers simultaneously, which is invaluable for building complex molecules.
Pattern 3. Chelation control with specific substrates and Lewis acids, high predictability overrides other effects.
You've got it. And finally, the fourth theme, which we touched on with PIN, is stereoconvergence due to reactant or product equilibration.
Where you get the same outcome regardless of starting E or Z.
Exactly. This is a fascinating phenomenon where, regardless of whether you start with the E or Z isomer of an allylic reactant, you often end up with the same product composition or the same major stereoisomer. This happens because there might be an intermediate step in the mechanism, perhaps transmetallation or just isomerization of the starting stannan or silane itself under the reaction conditions, that allows the E and Z forms to interconvert or equilibrate before the bond-forming step.
So they scramble before they react.
Or, alternatively, it can occur if the final stereoisomeric products themselves can equilibrate after they are formed, maybe via retroaddition and readdition, driving the reaction towards the thermodynamically more stable product. It means the starting stereochemistry might not dictate the final outcome, as the system finds its preferred pathway through an equilibration process. This is particularly common with the more reactive organotins.
Pattern 4. Stereoconvergence, common with tin. Starting geometry gets lost due to equilibration.
Those are the main themes. Of course, reality is always nuanced, but thinking in terms of these patterns, cyclic, open, chelated, or equilibrating, provides a really strong framework for understanding and predicting these crucial reactions.
That's a truly brilliant synthesis of these complex concepts. It sounds like the final stereochemical outcome is a sophisticated dance between the fundamental nature of the organometallic compound, whether it's boron, silicon, or tin, the specific Lewis acid chosa, and the precise structural and electronic features of the reactants themselves. Is it fair to say that understanding these few overarching principles gives chemists an almost predictive superpower for building molecules?
Exactly, or at least a much better ability to make educated guesses and design experiments intelligently. The beauty of organic chemistry, and particularly these carbon bond-forming reactions, lies in understanding these underlying principles. It allows chemists to not just perform reactions, but to precisely design and predict the outcomes of molecular construction, piece by intricate piece. It's about building molecules with purpose and precision, knowing that these predictable patterns unlock immense potential for creating new materials and medicines.
That was an incredible journey through the world of carbon bond formation using boron, silicon, and tin. From the elegant simplicity of how boron can extend a carbon chain one atom at a time with retention of configuration, to the intricate dance of stereoselective additions that silicon and tin allow, especially using chelation or chiral catalysts in complex natural product synthesis. It's abundantly clear that these elements are absolutely indispensable tools in a chemist's arsenal.
They really are foundational.
They provide the control and versatility needed to create compounds that impact everything from the drugs we take, which need that precise 3D shape, to the advanced materials that shape our world.
We've seen how subtle changes, switching from boron to silicon, changing a Lewis acid from BF3 to SnCl4, adding a nearby oxygen, using a chiral catalyst, how these subtle changes in the choice of reagents or reaction conditions can dramatically alter a reaction's outcome, leading to incredible control over molecular architecture.
It really highlights the elegance and precision possible in modern organic chemistry.
Absolutely. Enabling the construction of molecules with a degree of complexity that was unimaginable just a few decades ago. It's a field where mastery of the fundamental molecular interactions, like these transition state models, leads directly to tangible innovation.
It makes you wonder, doesn't it? If we can achieve this level of precision with elements like boron, silicon, and tin, what other hidden nuggets of knowledge are out there, maybe using other main group elements or new catalytic systems waiting to be unearthed, that could further revolutionize how we build molecules?
That's the exciting part, isn't it? There's always more to discover.
What new catalysts or conditions might unlock even greater control, allowing us to build molecular machines or synthesize even more complex biological structures with unprecedented efficiency and precision? The possibilities really feel endless when you start to see the fundamental building blocks this clearly. Thank you for joining us on this deep dive into the foundational reactions of organic synthesis using boron, silicon, and tin. We hope you feel a little more well-informed and hopefully a lot more curious about the invisible molecular world that shapes our lives.
It's been a pleasure. Until next time, keep exploring, keep questioning, and keep diving deep.